Swayam Prabha. Digital India. Educated India.
Welcome friends to this third lecture of week 9 of this NPTEL online certification course of environmental soil chemistry, and in this third lecture we will be talking more about some environmental pollution issues. We will be talking about acid rains and also alkaline soils and gypsum dissolution. But before going to discuss those things, I would just like to give you a quick recap of whatever we have discussed so far. So, in our first two lectures, we have started with the discussion with the pollutants in soil solution. I showed you this slide where I showed you that how the free pollutant concentration in soil solution shows different dynamics, and they can be converted to different forms and vice versa. I have shown you this pollutants in soil solution. Then we have discussed what are the dynamics of heavy metal pollutants in soil solution. We have discussed how heavy metals are present in a varying levels in groundwater, in especially as Indian states and union territories are concerned. Then we have talked about in details about the acid base equilibria. We have seen the relevant reaction for one acid one base, and then we have seen more complex of two bases and two acids, and how this corresponding equilibrium condition changes for these complex two acids and two bases reaction. Then we have discussed what is the importance of these hydronium ions H3O plus as far as the dissociation of acids are concerned, and also we have discussed about the pKa value. Remember, pKa is the negative logarithm of the acid dissociation constant Ka. So, a lower pKa value indicates a stronger acid. And we have seen the example of acetic acid and lactic acid, where the lactic acid has a lower pKa value, and as a result lactic acid is more stronger than lactic acid is stronger than that of acetic acid. Now, if you consider we have also discussed precipitation dissolution reactions, and we have seen different conditions of precipitation and dissolution. What is the condition of getting precipitation, what is supersaturation, what is undersaturation? We have discussed all these things. And then in terms of this dissolution of in water of an electrolyte comprising these cations and anions, we have discussed this example in terms of the solubility product constant and the activities of those anions and cations. So, we have seen that ion activity product, how these ion activity products linked with this solubility product to infer whether the solution when there will be oversaturation or saturation or undersaturation, and in these three conditions how these precipitation and dissolution will occur. Then we have seen the relationship between pH and concentration. I have shown you the zones of undersaturation, zones of oversaturation, as well as the metastability limits and metastable zones. Then we have started you discussed a important aspect, that is effect of mixed solvents and surfactants. We have discussed the structure of the surfactants and how their solubility, how they act as a dispersing agent to increase the solubility of nonpolar molecules in the water. So, what is their implication as far as the solubility of toxic organic chemicals like pesticides in water and their movement from one part of the environment to another part of the environment is concerned. We have discussed in details. Then we have seen the effects of mixed solvents and surfactants. We have discussed when there is a co-solvent in the water, how this mixture affects the solubility of a third substance. We have discussed this in terms of this relationship between the solubility in a mixture of solvents, which is basically the summation of solubility in pure water plus this this component, that is sigma s sigma Fs, where the sigma s is basically taking this form A log of KOW, where KOW is the organic solvent water partition coefficient and A and B are basically the empirical constant depend on co-solvent properties. So, we have discussed about the co-solvent, and based on that what are the possible composition of this solute mixture we have discussed. Then we have discussed the solvent and surfactant interactions, how these hydrophobic tails are extended into the interior of the cluster. The hydrophilic heads are oriented to the exterior in contact with the water phase, and how they affect the dissolution of nonpolar compound in the polar water solvent. We have discussed all these things, and also finally, we have discussed the temperature effect in the solubility. Remember that the solubility in water of the most inorganic and organic pollutants increases with the temperature, and the temperature not only has a direct effect on chemical solubility of the in the soil aqueous phase, but also has an indirect effect on the reactions. So, today we are going to start with the acid rains, detailed discussion about the acid rains and how they interact with the soil system, and what is the relationship between acid rain and soil system. So, a classical example of man induced effect on the acid base equilibrium in the soil liquid phase is the acid rain effect. Now, we have already briefly talked about the acid rain effect in our previous lecture. Remember that when there is an acidic precipitation, and this acidic we call it acid rain, and this acidic precipitation generally occurs when there is a reaction of different gases with the water vapor which is present in the atmosphere, creating different acids. So, acidic precipitation can be caused by natural volcanoes, as you can see it is natural volcanoes, and man-made activities. So, man-made activities, what are the man-made activities? So, they can be these gas can generate, for example, sulfur dioxide. This sulfur dioxide can be generated from the car exhaust, and in the also generation of the electricity also they can produce these gases. So, these acidic these gases when go to the atmosphere and mix with water vapor, then they produce the acidic rain. Now, the precursors of acid rain formation results from both natural sources such as volcanoes and decaying vegetations, and man-made sources, primarily emission from sulfur dioxide, and this sulfur dioxide basically emit from different automobiles. And nitrogen oxides, the nitrogen oxides can be represented as NOx resulting from fossil fuel combustion. So, this when we burn the fossil fuel, either petroleum or coal, they basically generate the sulfur dioxide and nitrogen oxides. And this sulfur dioxide, as you can see, these acidic gases released into the atmosphere, and for example, sulfur dioxide, nitrogen dioxide and carbon dioxide. They can be also generated from the smokestack of industrial release. So, gas carries to after their release, these gases carried upwards by the wind and goes combined with the water droplet to form different acids. So, we are going to see the chemical reactions which are responsible for forming those acids, and ultimately they come back ultimately in the form of acid rain. So, acid rain basically what happens when there is an acid rain basically destroy plants, pollutes water sources and erode different buildings, and so these are some of the ill effects of the acid rains. So, we have seen that the precursor of this acid rain formation, mainly the gases sulfur dioxide and nitrogen oxides are forming as a result of fossil fuel combustion. So, the burning of these fossil fuels like coal and petroleum by power production companies, as we are seeing here, power production companies and industries release this sulfur into the air and combines with the oxygen in the form of sulfur dioxide. So, that is how this sulfur dioxide gas is produced. Now, exhaust from the cars cause the formation of nitrogen oxides in the air. From these gases, airborne sulfuric acid, for example, from this sulfur dioxide, these airborne sulfuric acid and nitric acid. This nitric acid can form from these nitrogen oxides, can be formed and dissolved into the water vapor in the air. So, these are some of the reactions which are responsible for producing the acid rains. So, let us see. So, sulfuric acid and nitric acid are the major agents of the acid rains. They are the strong acids. So, let us consider the formation of sulfuric acid. As we have seen that sulfur dioxide, this sulfur dioxide which is produced by burning of the fossil fuels, when they exhaust and then basically reacts with the oxygen to form sulfur trioxide. So, this sulfur trioxide when reacts with the water vapor, they will produce H2SO4 or sulfuric acid. Similarly, formation of nitric acids, here you can see nitric oxides. These nitric oxides when reacts with the oxygen, they produce N2O5, and these N2O5 when reacts with the water vapor, they produce this nitric acid. And so, hydrochloric acid, nitrous and then nitrous acid and carbonic acids are also can contribute to acid rain. So, major contributor of these acid rains are sulfuric acid and nitric acid. Apart from that, hydrochloric acid, nitrous acid and carbonic acids also contribute to acid rains. How carbonic acid fall is generated? This carbonic acid is generated because of the carbon dioxide reaction with the water vapor. As you can see here, the carbonic acids, carbon dioxide when reacts with the water vapor, it produces the carbonic acid. Formation of nitrous acids. So, here you can see nitric oxides, when it reacts with the ozone, it produces nitrogen dioxide and oxygen, and these nitric oxides also can react with this nitrogen dioxide to produce this N2O3, and this N2O3 when reacts with the water vapor, it produces this nitrous oxide. So, what we can see? We are seeing that the sulfur dioxides or the nitrogen oxides which are exhausting from which are emitting due to the industrial activities as well as the burning of the fossil fuels or car exhaust anthropogenic activities, they basically undergoes different reactions, chemical reactions, and ultimately they reach into the atmosphere, mix with the water vapor and then form the acid and comes back into the soil in the form of acid rain. Now, if an acid rain reaches alkaline soils, the rain acidity is neutralized by the existing bases and the pH of the soil solution remains unchanged. So, again if so to simplify this, when the acid rain which is basically acidic in nature, when reaches the alkaline soil, the rain acidity is neutralized because of the presence of the bases in the alkaline soil by in the alkaline soils, and pH of the soil solution remains unchanged. So, there is basically neutralization. Where the buffering effect is lacking, let us consider a soil where the buffering effect is for example, the soil which has low amount of clay or low amount of organic matter, these soils are lacking their buffering capacity. So, when there is an acid rain in this type of soil, the acid rain induces an increase in the acidity of the soil. So, although acid rain gases may originate in urban areas, they are often carried for hundreds of miles in the atmosphere by winds into the rural areas. That is why forests and and lakes in the countrysides or rural areas can be harmed by acid rains that originate in the cities. As you can see here, this is a photograph of acid rain effect in the forest, which is published by USGS. So, you can see this due to the acid rain, a large tract of forest area are getting affected and plants are getting defoliated. So, this is basically the interaction of acid rains in the soil solution. So, if you see the pH of the acid rain. So, obviously, these chart or these graph will give you better idea, this chart will give you better idea. So, we can see in case of battery acid, which is highly extremely acidic, the pH will be 0, whereas liquid rain cleaner which has the highly basic are having the pH 14. When we are talking about pH 7, that is the pH of a pure water. So, if you consider the acid rain, this acid rain has a pH varies from 4.2 to 4.4, and so basically near about pH 4 we can see the the pH of an acid rain. So, basically this acid rain is highly acidic, and as a result of this very low pH, all fish which are present in the aquatic body basically dies. So, so this is basically giving an idea about the pH of the acid rain. So, the environment can generally adapt to a certain amount of acid rain, and often soil often the soil is slightly basic due to the naturally occurring limestone which has a pH greater than 7. Now, because bases counteract the acids which I have already discussed in the last slide. So, bases basically counteract acid, and this soil tends to balance out some of the acid rain's acidity, but in areas where limestone does not naturally occur in the soil, or in the areas where the soil lacks the normal buffering capacity, acid rain can harm the environment, as you can see here. So, let us talk about another important thing. So, we have completed the acid rain. Let us talk about another important thing, that is aluminum dissolution. Now, aluminum is a aluminum is a element which you can see, or aluminum is a metal which you can see in high concentration in acidic condition. Now, remember that the dissolution of aluminum is the main consequence of acid atmospheric deposition in forest soils. So, increase in ionic concentration of aluminum in soil solution has adverse effects on soil biology and crop development. So, basically again the dissolution of aluminum is the main consequence of acid atmospheric deposition of forest soil. As a result of acid deposition or acid rain, the aluminum activity in the soil solution quite increase, and these increased ionic activity of aluminum has an adverse effect on soil biology and crop development. This picture can give you a better idea about the ill effects of aluminum concentration in the soil solution. As you can see here, these are the roots which are grown with an aluminum concentration of less than 2 ppm, whereas and here here the aluminum is here 15 ppm. Now, here the difference basically is here in this case we are applying 1 ton per hectare lime, and here we are not applying lime to neutralize the acidity. So, obviously, when we are adding lime to neutralize this acidity, we can see that there is normal growth of the roots. However, when there is no application of lime, obviously their concentration of aluminum increases, which adversely affect the root growth, which you can see in this picture. So, it is observed that the logarithm of aluminum dissolution rates in the individual soil samples followed an inverse linear relationship with pH. Now, remember that together with pH, organic matter has been shown to influence the aluminum dissolution. How? Let us see in our next slide. So, this graph basically shows the relationship of aluminum concentration in microgram per ml and pH. So, here basically this graph is showing aluminum dissolution from aluminum organic matter complexes. So, one thing is clear that aluminum concentration in solution reaches a minimum value in a pH range of about 4 to 5. So, in this region the aluminum concentration in the solution reaches a minimum value. Now, above this pH 5, the concentration of the aluminum above this pH 5, the concentration of the aluminum in solution increases dramatically. As you can see, it is increasing with a steep slope, and it is clearly observed that aluminum organic matter is solubilized in the pH range of 5 to 7. So, obviously, when there is a solubilization, aluminum concentration in the soil solution will increase, and this experimental finding confirms with previous work of aluminum availability with the plants. So, this basically shows the aluminum dissolution from aluminum organic matter complexes, and how this dissolution of this aluminum from these aluminum organic matter complexes are influenced by the pH of the soil solution. So, another important thing which we need to discuss is the alkaline soils and gypsum dissolution. Now, you know what are the alkaline soil? Alkaline soils are those soils in which the exchange complex is saturated with the sodium ions, and as a result of the saturation of the sodium ions, the soil becomes alkaline in nature. The alkaline soil are having high pH, and the alkali soils or alkaline soils are not good for crop production. Why? Because they have unfavorable physical conditions. What are those unfavorable physical conditions? Due to the presence of sodium, the soil particles are dispersed, they do not form the aggregates, and as a result of that the zeta potential is quite high. As a result of high zeta potential, the flocculation never occurs, and these individual particles basically block the entry of moisture or soil water through infiltration or exchange of gases from the atmosphere to the soil layer, and as a result of that, these alkaline soils are not good for crop growth. So, these alkaline soils need to be reclaimed, for the reclamation of these alkaline soil, the farmers generally use gypsum, which is basically calcium sulphate dihydrate, and since the salinization or alkalinization could affect the soil properties as well as the gypsum balance. So, the distribution of gypsum depends on the natural constituents or on the human activities. So, generally to counteract the ill effects of alkaline soil, we generally apply gypsum. Gypsum is basically calcium sulphate dihydrate, and the gypsum, the calcium from the gypsum can replace the sodium in the exchange complex, and as a result the clay starts to flocculate or forming the aggregate. So, that is why we generally apply the gypsum in the alkaline soil. As you can see here in this picture, farmers are spreading the gypsum, dusted gypsum in the alkaline soil. So, the dissolution, let us consider the dissolution of the gypsum in the alkaline soil. So, the dissolution of the gypsum in the alkaline soil profile could be change as a result of alkalinity. Now, the effective solubility of gypsum basically depends on the soil solution and exchange phase composition. So, let us see how it occurs. So, the dissolution exchange reaction, as you can see. So, the exchange complex was previously saturated by sodium ions. So, let us consider these two sodium ions was attached or adsorbed into the clay surface, and when we are applying the calcium sulphate, the calcium basically replaces this sodium, and which basically comes into the soil solution. So, as a result of that, the calcium binds the soil particles and forming the aggregate. So, the sodic soils or alkali soils are basically the sodium saturated soils. So, irrigation with sodic water, if we just do the irrigation with sodic water, brings an increase in the exchangeable sodium in the soil complex and creates the unfavorable condition, as you can see in this picture. And so, under such conditions, the dissolution of calcium sulphate will increase to compensate for the sodium which is exchanged with the calcium in the soil. As you can see, this is an ill effect of of the sodic soil. As you can see here, the exchange complex has nil sodium. Here it has got slightly higher sodium content, and in this condition they have moderate sodium concentration in the exchange complex, and here it has severe sodium concentration in the exchange complex. So, as you can see from this slide, from this soil to this soil, there is a continuous increase in sodium concentration. As a result of that, you can see here the degree of dispersion is continuously also increasing with the increase in sodicity. So, here this soil is highly aggregated, and these soils are increasingly disaggregated. So, under such conditions, when these when the sodicity is increasing in the soil, the dissolution of calcium sulphate is also increased, because this calcium from this calcium sulphate competes from the exchange side in the soil and thereby replace those sodium from the exchange side to form the aggregates or to form the flocculates. So, this is basically the dissolution of gypsum in sodic soils. It has been reported that effective gypsum solubility is enhanced through ion pair formation and electrolyte effects. Under these conditions, the amount of water required for dissolution of gypsum in alkaline soil is likely to be much less than commonly inferred from gypsum solubility in water. Again, the effective gypsum solubility is enhanced through the ion pair formation. What is ion pair? We will discuss, and the electrolyte effects. In these conditions, the amount of water which is generally required for dissolution of gypsum in alkaline soil, here will require much less than commonly what we see which is required for gypsum solubility in the water. So, let us wrap up our lecture here. In this lecture, we have discussed the acid rain effect and their interaction with the soil system. Also, we have seen the sodic soil and how the gypsum solubility is influenced in the sodic soils, and also we have seen the aluminum solubility from the organic matter complexes, aluminum organic matter complexes, and how they are impacted by variable pH. So, I hope that you have learned something new in this lecture. Let us wrap up this lecture here, and the next lecture will be discussing more about ion pair effects. What is ion pair, which we have discussed here, what is the ion pair, and other aspects of pollutant and soil solution interactions. So, feel free to email me or feel free to let me know if you have any questions. I hope that these are pretty self-explanatory. If you need any explanation, just let me know and feel free to email me. I will be more than happy to answer your queries. Thank you very much. Let us meet in our next lecture.